Okay, good morning friends. On the previous session actually we just start the boilerplate basic portion. So now we'll continue that particular basic portion of the boilerplate. Okay. Now in the previous sessions g of s which is equal to 1 plus st. Now this is in a time constant form. If it is in the time constant form, you are saying that the corner frequency is 1 by t radians per second, and we will see the corner frequency definition also. What is the corner frequency? Corner frequency is the frequency where the slope is changing from one level to another level. Now at that particular corner frequency, the slope is changing from one level to another level. Now this is the 1 plus st. It is having some corner frequency, and if it is having some corner frequency and that 0 is on the left hand side of its plane, now this is called as simple 0. This is called as a simple 0, or also called as a finite 0. Now this is called as a simple 0 or a finite 0. Then what we are covered in the previous session, now for this particular simple 0, for this particular finite 0, then you are try to draw the Bode magnitude plot, which we are already finished it. Okay. Now what you are getting, the Bode plot you are getting like this: the magnitude of open loop transfer function in terms of dB versus frequency. But what we are getting now, when omega t is far less than 1, when omega t is far less than 1, slope is, when omega t is far less than 1, slope is 0 dB per decay. When omega t is far less than 1, slope is 0 dB per decay. But when omega t is far greater than 1, when omega t is far greater than 1, slope is plus 20 dB per decay. When omega t is far greater than 1, slope is plus 20 dB per decay. Okay, this we already see the proof of this. Okay. Now when omega t is less than 1, 0 dB per decay. When omega t is greater than 1, 20 dB per decay. Now this particular transition frequency, when omega t equal to 1, means omega equal to 1 by t. This is the frequency where the slope is changing from one level to another level. That particular frequency is called as corner frequency. This particular frequency is called as corner frequency. Corner frequency is the frequency the slope is changing from one level to another level. The corner frequency is the frequency the slope changes from one level to another level. That particular frequency is called as corner frequency. Now students, now this is the Bode magnitude plot of one simple 0, one finite 0. Okay, but the Bode plot is an approximated plot. Therefore we consider the slopes, we consider the phases after the corner frequency. Now after the corner frequency, how much is the slope? That should be the slope is considered for a simple 0 or a simple finite 0. Okay. Now what is the slope after the corner frequency? Now therefore this is plus 20 dB per decay should be the slope which we want to consider for this particular simple 0. So one simple 0, then the slope is plus 20 dB per decay. Now I am asking one question. Now this is one simple 0 or one finite 0. This is a situation, am I not? One simple 0 or one finite 0. Now this is the situation. If this is 1 plus st whole square, if it is 1 plus st whole square means what? If it is 1 plus st whole square means two simple zeros or two finite zeros, am I right not? Now the students, it is two simple zeros or two finite zeros. Now two simple zeros or two finite zeros is nothing but, now previously it is 0 dB per decay, but 2 is nothing but here 2 into 20 means 40 dB per decay. Now the slope is changing from 0 to 40. At which particular frequency? At the same frequency, and that particular frequency is called as corner frequency. The slope is changing from one level to another level. Now that particular frequency is called as corner frequency. Understand? Corner frequency will be same. What is the definition of corner frequency? At that particular frequency, the slope is changes from one level to another level. So this is we are taking for one simple zero or one finite zero in the previous session, and this should be approximated to plus 20 dB per decay. Understand or not? Can note on this. Now see here. Now we will finish the BOD phase plot also this, such that we can find one table for it. Now in the same, g of j omega which is equal to 1 plus j omega t. Now actual phase is completely depends upon the frequency, tan inverse imaginary part by real part. It is completely depends. It is completely depends upon frequency. The actual phase is completely depends upon frequency. So it is not possible for finding the phases by substituting all the frequencies, right? Now that's why then we will take an approximation when omega t is far less than 1. When omega t is far less than 1, g of j omega which is equal to, when omega t is far less than 1, neglect 1. Now this is 0 plus, where omega t is far less than 1, so if you neglect omega t, now this is 1 plus j0. Then what is the phase? Now the phase angle is tan inverse imaginary part by real part. Tan inverse imaginary part by real part, tan inverse 0 is 0 degrees. Now when omega t is far greater than 1, now g of j omega is, when omega t is far greater than 1, now neglect 1, now 0 plus j omega t, then the phase angle is the angle of g of j omega, which is nothing but tan inverse imaginary part by real part, therefore which is nothing but tan inverse infinity, which is nothing but plus 90 degrees. Plus 90 degrees. Therefore, now again, the phase angle versus frequency, if you take it, now this is angle of j omega in terms of degrees. When omega t is far less than 1, what is the phase? 0 degrees. Now this is 0 degrees. Now then when omega t is far less than 1. But when omega t is far greater than 1, now the phase is 90 degrees. Now this is when omega t is far greater than 1, the phase is 90 degrees. When omega t is less than 1, phase is 0 degrees. Okay. Now this is also same. One simple 0, now the phase is plus 90 degrees, and this should be considered after the corner frequency. Therefore, this should be approximated that the phase of one simple 0 or one finite 0 is plus 90 degrees. Understand or not? Now, similarly, if it is a two finite zeros or two simple zeros, now this is square, so this is 0 degrees. So this is square means this is 2 into tan inverse infinity, 2 into 90 degrees. Understand or not? So before and after, But while we are drawing the BOD plot, we consider the approximated value. The approximated value is to be considered after the corner frequency. Now after corner frequency, what should be the phase? And after the corner frequency, what should be the slope? Now that we have to be treated the slope and phases for that particular zeros or for that particular poles. Okay. Now this is the way you can easily understand what is corner frequency. Now if it is a 0 plus 90 degrees is phase. If it is a pole minus 20 or minus 90 degrees, you already know that. Okay. Now you just note down this. Now, if you understand this, then we will take this is for n simple zeros or n finite zeros. We will extend it the same thing for n. Now see here, 1 plus st whole power n. Now this is n simple zeros or n finite zeros. N simple zeros or n finite zeros. Now if it is n simple 0 or n finite 0, now the slope is, what is the slope? Slope is nothing but n into plus 20 dB per decay. What is the phase? Phase is n into plus 90 degrees, but it is depends upon frequency because we can take it an approximated phase. Okay. But whatever it may be, but the corner frequency is 1 by t radians per second, because at this particular corner frequency, the slope may changing from 0 to 20 or 0 to 40 or 0 to 60. The slope changes from one level to another level is called as corner frequency. Okay. So this is for n simple 0 or for n finite zeros. Now if you understand this, can you tell me for this? G of s, which is equal to 1 plus 1 by 1 plus st whole power n. Now this is nothing but, what is this? Now this is nothing but n simple poles. N simple poles or n simple poles or n finite poles. N simple poles or n finite poles. Now this is n simple poles or n finite poles. Now the slope is n into n simple poles or n finite poles, slope is n into minus 20 dB per decay, and phase is n into minus 90 degrees. Here is also it is depends upon frequency, and whereas the corner frequency is whether it is a pole or zero. What the definition of corner frequency is what? The corner frequency is the frequency where the slope is changing from one level to another level. Previously 0 will become 40, 0 will become 20, 0 will become 60, yet omega c equal to 1 by t. Now 0 will become minus 20, 0 will become minus 40, 0 will become minus 60, where is at same corner frequency. So the corner frequency is the frequency where the slope is changing from one level to another level. And don't by heart the corner frequency, where the slope is changing from one level to another level. Now that particular frequency is called as corner frequency. And students are asking one more doubt. Sir, 0 will become 40 or 20 will become 0 will become 60 like that? No, I am not saying 0 and 40. In our example, I am saying like this. Now 20 will become 60 or 60 will become 100, 100 will become 120, 120 will become 40. Like that, the slope is changing from one level to another level only at particular frequency. That particular frequency is named as corner frequency. Now this is n simple 0 or n finite zeros. Clear or not? Then you can easily understand what is the slope, what is the phase for zeros, poles and zeros at origin, poles at origin, simple zeros, finite zeros, simple poles, finite poles. Then you can easily draw the BOD plot. Okay, just take down this. Now, if you have all these things and the BOD plot drawing, which is a very simple. Now I am asking one more question. G of s, which is equal to s square plus 2 zeta omega n into s plus omega n square. And most of the students are thinking that this is the characteristic equation, means poles. Therefore, they are saying that minus 20 dB or minus 40 dB or minus 90 degrees or minus 180 degrees. That is wrong. Now, that is a characteristic equation or not, all these things we don't know. We know only one thing. It is a numerator polynomial or it is a denominator polynomial. If it is a numerator polynomial 0, denominator polynomial pole, that is the only thing. Okay. But this is the numerator polynomial zeros. Now, the power is 2. Therefore, polynomial power is 2. Therefore, there are 2 roots. Therefore, 2 zeros. I mean, is it right or not? If there are 2 zeros, then what is the slope? Now, the slope is 40 dB per decay and phase is minus plus 180 degrees. But the problem with the corner frequency, while finding the corner frequency, first it should be converted into time constant form. 1 plus 2 zeta s by omega n square, omega n is cancelled, and plus s square by omega n square. S square by omega n square. And again, replace s equal to j omega. Find real part, find imaginary part. Again, same concept. Greater than 1, far greater than 1, far less than 1. Like that, you can do the derivation part. You can get the answer. But without doing the derivation part also, I'll try to find one simple shortcut method. For finding the corner frequency for a polynomial of as square plus bs plus c. Like this. Okay. If it is a quadratic equation, if it is a polynomial of as square plus bs plus c, in such a kind of characteristic equations or polynomials are available, then first you convert it into the time constant form and see always the denominator of s square. Now s square coefficient, now whatever the value in the s square, now this is s square coefficient, the denominator value is omega n square. From here we want to find, from here From here we want to find corner frequency. From here we want to find corner frequency. Even if you go for the long derivation part, previously how I am mentioning, replace S equal j omega. Real part, imaginary part you separated. Find the magnitude, and omega far greater than 1 is one case, far less than 1 is one case. Then what should be the answer we are getting? That answer I will tell you directly in a shortcut method. So for getting that answer, always you concentrate on SS square. Okay. Now whatever the value in the SS square, from there you want to find the corner frequency, and from here corner frequency is omega n radians per second. From here you want to find the corner frequency, and it should be 1 omega n radians per second. For easy understanding, I will take one simple problem such that you can easily understand. Let us take one problem is S square plus S plus 32. Okay. Now this is the same polynomial. So what I am saying, first convert it into time constant form, 1 plus S by 32 plus S square by 32. What I am saying, after writing like this time constant form, see always S square value for finding the corner frequency. What is the S square value in the corner frequency? Now this is nothing but omega n square. What is this? This is nothing but omega n square. Omega n square equal to 32. From here we want to find corner frequency. Now from here we want to find corner frequency. Now that is omega n square, but the corner frequency is omega n. So omega c, which is equal to omega n, which is equal to root 32 radians per second. From here we want to find the corner frequency. Omega n square equal to 32, omega n equal to root 32. Now this is the corner frequency. Okay. If it is a polynomial form, if it is a quadratic equation form, then you can find the corner frequency like this, whether it is a 0 or whether it is a pole. Okay. Now the remaining two parameters which are very simple. Now what is the slope? Then it is very easy. The slope is 2 into, because this is 2 zeros, 2 into plus 20 dB per decay, which is nothing but 40 dB per decay. And phase which is equal to 2 into plus 90, which is equal to plus 180 degrees. Okay, note on this. Okay. Now very simple. Now if it is a pole, then it is very easy. Your answer will be same. Once if you understand 0, you can easily say finding for pole. Now this is a pole. Now this is your transfer function. Now this is the pole. Now this is only saying 1 divided by, that's it, right? Now this is same. Corner frequency is same. Now, but the slope is, now this is minus 40 dB per decay and phase is minus 180 degrees. That is the only change because this is the poles, right? This is the poles. Okay. Take this one also. So if the quadratic form poles and zeros are available, now if it is in the form of as square plus bs plus c, and use this particular procedure to find the corner frequencies. Now the students, now you know how to find slope, you know how to find corner frequency, and you know how to find phases. If these three parameters are available, you can easily draw the BOD plot. Okay. So 0 plus 20 dB per decay, poles minus 20 dB per decay, zeros plus 90 degrees, poles minus 90 degrees. If it is in the 1 plus st form, time constant form, and poles and zeros on the left hand side of a plane, it is having some corner frequency, and the corner frequency time constant relation is always inversely proportional. If it is like a quadratic form, and I am already saying how to find the corner frequencies in a shortest manner, use that one. And if you want to see that is correct or not, and you do the procedure, you already know the procedure, then if you solve the procedure, then you can get the same answer. Okay. So now what I am doing is, now let us take one simple problem, and we will try to draw the BOD plot for that particular question. Okay. Now the transfer function is, draw the BOD plot by considering the transfer function g of s, which is equal to 10 cube into s plus 10 by s square into s plus 1 whole square into s square plus s plus 10. This is the transfer function, student. This is the transfer function, and what he is saying is, now draw the BOD plot for the given transfer function. Okay. Now I will take a step by step. Here I will write the steps, and here I will follow that steps, and I apply that steps to this particular problem, and finally we can get the BOD plot. Okay. Now I will write here steps. What are the steps? Now let us take the first step one. Now the step one is, time constant form, and which results system gain and corner frequencies. Okay. What is step one? In the shortest manner I will write. Now the step one is, first to find the system time constant, first to convert the given transfer function into time constant form and identify given transfer function into time constant form and identify gain and corner frequencies. Convert the given transfer function into time constant form and find the system gain and corner frequencies. But this is the pole zero form, s plus p, s plus z, s plus p means pole zero form. Now convert the transfer function into time constant form, means take all constants as a common. G of s, which is equal to, now take here 10 as a common. Now therefore this is 1 plus s into 1 by 10. And here 1 is common, here is also 10 is common, and s square into 1 plus 1 into s, and 1 plus s by 10 plus s square by 10. 1 plus s by 10 plus s square by 10. Now these are the time constant form, 1 plus st form. Now k into 1 plus st1 into 1 plus st2 into and so on by s power n into 1 plus sta into 1 plus STB into and so on. Now 1 plus ST form, time constant form. Now you just compare what is the system gain. Now the system gain 10 cancel. The system gain is 10 cube. Okay, system gain is 10 cube 1000. And corner frequency is 1 plus ST form. T equal to 1 by 10. 1 plus ST form. T equal to 1. Now this is omega n square. I am giving one shortcut method. Omega n square, which is equal to 10. So now the corner frequency and time constant is inversely proportional 1 by 1 by 10, which is equal to 10 radians per second. 1 by t, which is equal to 1 by 1, which is equal to 1 radians per second. And corner frequency is omega n, which is equal to root 10 radians per second. Now these are the corner frequencies and time constant is inversely proportional. Okay. Now the step 1 is completed. First identify the system gain and corner frequencies. Okay. Now identify system gain and corner frequencies by converting the given transfer function into time constant form. Now this is the result 1, step 1 result. Okay. But the next time, this is the procedure, but the next time you don't do this procedure. Okay. And I'm giving one shortcut method also, you see. If it is a pole 0 form, means S plus Z or S plus P form. If it is a pole 0 form, that P or that Z, that 0 or that pole is directly a corner frequency for that particular simple 0, for that particular simple pole. Now, meaning is S plus Z, this itself is called as a corner frequency in a shortcut method. S plus Z, therefore omega C, which is equal to 10 radians per second directly. S plus P, now this P is directly the corner frequency omega C, which is equal to 1 radians per second. And this you already know that omega n square, and from here you can find the corner frequency, which is nothing but root 10 radians per second. Now 10 radians per second, 1 radians per second, root 10 radians per second, these are the corner frequencies for this particular zeros and for that particular poles. Okay. Now this is the zeros and poles, and you can easily get the corner frequencies. From the next time onwards, these steps are removed and you can take directly the corner frequencies. And system gain also you can find directly. The system gain is nothing but numerator constants by denominator constants. The system gain is nothing but numerator constants by denominator constant, which means that simply substituting the transfer function s equal to 0, whatever the constant you are getting, that is the answer. So, and here in the shortcut method, the k equal to numerator constants by denominator constants. Numerator constants by denominator constants is nothing but system gain k 10 cube into 10 by 1 into 10. 10 cancel, which is equal to 10 cube. This is the numerator constants by denominator constants is the system gain k directly. Okay. From the next time you remove all these steps, you just follow these 2 steps and step 1 is finished. Okay. Now first you just take first step 1. Okay. Now this is the step 1 for any problem. Okay. These are the steps. Okay. And now step 1 is not required, and you can easily get the shortest way to get those step 1 result. Now the step 2 is, identify poles at origin, or zeros at origin. Identify poles at origin or zeros at origin. Now see, now in this transfer function there are 2 poles at origin. Yes, there are 2 poles at origin. There are 2 poles at origin, 1 by s square. If it is zeros at origin, sir, there are 2 zeros at origin. If it is a poles at origin, sir, there are poles at origin. Sir, there is no poles at origin, there are no zeros at origin. Whatever it may be, you first identify. Okay. Now this is step number 2. Now step number 3. Now the step number 3 is starting slope. What should be the starting slope? Starting magnitude. In y-axis, where we want to start the plot. In y-axis, where we want to start the plot. Okay. Now the starting magnitude of any BOD plot is, the starting magnitude in terms of dB, the formula is 20 log k base 10 plus or minus n into 20 log omega base 10. Okay, where k is system gain, you know that, where k is system gain, where omega is least corner frequency. Here k is system gain. K is system gain, where omega is least corner frequency. Okay. Now this is the formula for that, and now we'll consider for our problem. We apply the formula for our problem. Then what is the starting magnitude? Now the starting magnitude in terms of dB in our problem is 20 log k. What is k? K is already calculated. How much you are getting? K is 1000, 10 power 3, 1000 base 10. Now here plus or minus is available. Sir, what we have to consider? We consider plus or we consider minus. Okay. So that is the reason why now step 2 is how many poles at origin or how many zeros at origin. If it is a poles at origin, this is minus. If it is a zeros at origin, this is plus. So which means that this second part belongs to the number of poles or number of zeros at origin. Now in our problem there are 2 poles at origin, therefore minus n means how many? There are 2 poles at origin. 2 into 20 log base 10. Omega least corner frequency 1, 10, root 10. Among this, what should be the least corner frequency is 1. Therefore log 1 is 0. Now this 3 is nothing but 3 into 20, 60. Therefore plus 60 dB. Log 1, this is nothing but 0, and this 3 is 20. 3 into 20, 60. Log 10 base 10 is 1. So in our problem the starting magnitude is 20 dB per decay. Then you understand or not? This zeros at origin you have to consider plus. Poles at origin you have to consider minus. N means how many zeros at origin, how many poles at origin. So this second part belongs to number of poles, number of zeros, or number of poles at origin. Now the students are asking a question. Sir, there is no pole at origin, there is no zero at origin. What should we do, sir? If there is no pole at origin, if there is no zeros at origin, then you remove the second part. If no pole at origin, no zero at origin, then the starting magnitude is only 20 log k base 10. Understand or not? If there is no pole at origin, if there is no zeros at origin, there is no second part. If there is no second part, the starting magnitude in terms of dB is 20 log k base 10. Understand or not? Note down this. Okay. Now this is step 3. Now we'll see step 4. Now the step 4 is starting slope. Starting slope of the BOD plot. Now the starting slope is also decided by number of poles at origin or number of zeros at origin. That is the reason why we will put a separate case, identify how many poles or how many zeros at origin in the given transfer function. Now see here, the starting slope is nothing but the starting slope is the slope of, see the definition, the starting slope is the slope of number of poles at origin or slope of number of zeros at origin. Therefore, the starting slope is the starting slope, which is nothing but slope of number of poles at origin or slope of number of zeros at origin. Now here in our problem there are 2 poles at origin. 2 into what is the slope of each pole is nothing but minus 20 dB per decay. Therefore, which is nothing but minus 40 dB per decay. Understand or not? Suppose there are 2 zeros at origin. In our transfer function there are 2 zeros at origin. 2 into zeros means plus 20 dB per decay. Sir, in our transfer function only 1 pole at origin, sir. 1 into minus 20 dB per decay. Sir, in our transfer function there are 1 zero at origin, sir. 1 into plus 20 dB per decay. And the students are asking, sir, no pole at origin, no zeros at origin. No zeros or no poles at origin. If there is no poles or no zeros at origin, then the starting slope is 0 dB per decay. If it is a constant line, which indicates that the slope is 0 dB per decay, which means that no pole at origin, no zero at origin. If no zeros or no poles at origin. Understand or not? Now this is the step number 4. Starting slope is decided by the number of zeros at origin or number of poles at origin. If no pole at origin, no zero at origin, and the starting slope is 0 dB per decay. Now this is step number 4. Okay. Now we'll find step number 5. Now the step number 5 is final slope, because in BOD plot we want to consider the slopes. Now what should be the final slopes? Okay, Now the final slope for any problem is, any transfer function will have one shortcut method. The final slope is nothing but np minus nz multiplied with minus 20 dB per decay is the final slope. Now you already know that there are three kinds of transfer function. Practical transfer function, number of poles is always greater than number of zeros. Number of poles here 2 to 4 to 6 and number of zeros is only 1. NP is total number of poles, NZ is total number of zeros. Generally the transfer functions are practical transfer functions where poles is greater than zeros such that NP is greater than NZ. In such a situation you should take this as a formula. If it is poles is less and zeros are more, NZ minus NP, but don't multiply it with minus 20. Now there you multiply it with plus 20. Okay. If zeros are more, multiplied with plus 20. If poles are more, multiplied with minus 20. And if poles are more, NP minus NZ. If zeros are more, NZ minus NP, multiplied with plus 20. Poles are more, NP minus NZ, multiplied with minus 20. Okay. So this is the practical transfer function, and generally almost all are practical transfer functions. So final slope is NP, total number of poles 6 minus total number of zeros 1 multiplied with minus 20 dB per decay, which is nothing but 6 minus 1, 5 into minus 20, minus 100 dB per decay. Now this is the final slope, which is minus 100 dB per decay is the final slope. Okay. Now this is the final slope of this particular problem. The ending slope is this one. Now again also students are asking question, if number of poles is equal to number of zeros, if number of poles is equal to the number of zeros, now NP equal to NZ or NZ equal to NP, then the final slope is, if NP equal to NZ, which is nothing but, if it is a ideal transfer function, final slope is NP minus NZ, NP equal to NZ, now 0 dB per decay, if it is a ideal transfer function, or if it is a critical transfer function where number of poles and number of zeros are same. Understand or not? Yes. Now the next step, now step number 6, final phase. This is also useful while drawing the BOD phase plot. Final phase, very simple. The final phase which is nothing but, now NP minus NZ, which give minus 90 degrees. The final phase is NP minus NZ multiplied with minus 90 degrees. 6 minus 1 into minus 90 degrees, therefore, which is nothing but 5 into minus 90, minus 450 degrees is the final phase. Okay, minus 450 degrees is the final phase. This is the final phase which is useful for drawing the BOD phase plot. Okay, these are the steps which are required to draw the BOD plot. If these 5 steps are understand, then you can easily draw the BOD phase plot. Okay, now take down these steps, and this is very useful to solve any BOD plot.